Okay, we are going to be talking about inverses in section 7.1, namely the inverse of the sine, cosine, and tangent functions. I want to point out that once you start looking for inverses, you're looking for angles. We'll be looking for inverses in sections 7.1 and 7.2 in order to prepare you for section 7.3, where we will be solving trig equations. And again, you'll also be solving for angles. So these first three sections are all about solving those angles. The only difference between 7.3 and 7.1 and 7.2, which are on inverses, is that inverses have restrictions. Okay, so let me remind you of some things that you learned in algebra but may have forgotten. First of all, when something has an inverse, and you're going to find the inverse of any function, in order to be able to do so, that original function, you have to be able to pass a vertical line, and that vertical line should only cut through the graph one time. That's called the vertical line test. Every line test is like that, that whatever kind of line you're passing through the graph, it should only cut through it one time. If you're going to find an inverse, that original graph also has to pass the horizontal line test. So here I am presenting you with the original graph for y is equal to sine of x. Notice that it is cyclic and continues in a cyclic pattern. So it does pass any kind of a vertical line test. You could pass a vertical line, it would only cut through it once. However, you can see that this horizontal line that I have passed through the original graph, that it cuts through the graph once, twice, three times, and it will continue cutting through the graph over and over. So it fails the horizontal line test. So you can't find an inverse for the entire graph, but you can take out a portion of the graph, which I've highlighted in pink, but I've removed it for you over here. And you can find an inverse for just that restricted portion. Okay, now notice that some things here, again, we're talking about the original graph, and this is a portion of the original graph. We haven't found any inverses yet. I'm just getting you prepped for the restrictions that you're going to need in order to go on and move forward and actually find an inverse. Notice that the domain on this restricted portion is negative pi over 2 to pi over 2. That's what these x values are from here to here, negative pi over 2 to pi over 2. So that's called your domain. The y values on this restricted portion are negative 1 to 1. Now again, these are things from a portion of the original function. When you go into talking about inverses, the domain and the range switch. If you don't remember that from algebra, that is one of the characteristics of an inverse when you compare it to the original function or any portion of the original function. The domain and the range switch responsibilities. So that's why you're going to notice that although the domain was negative pi over 2 to pi over 2 here, from this portion of the original function, it now plays the role of the range. And these range values that were negative 1 to 1, they now play the role of the domain. So that is always true when you're talking about any portion of an original function and all of a sudden you start talking about inverses. What you're going to want to memorize is these restrictions in this form, because you're going to be handling finding the inverse yourself. So when I present you with an inverse problem, if it happens to be inverse sine, you are going to make sure that number one, that you have permission to proceed with this problem, and that'll be by you looking at the domain value in the inverse function. Have I given you something between negative 1 and 1? Because if I haven't, you may not proceed with the problem because the problem is undefined. Now, how can you get out of that? Just in case you forget what those values are, you can always put in inverse sine of whatever value I give here. And if you have forgotten what's too big or what's too small, you can put in your calculator, and your calculator will quit on you, just as it always does when you are feeding in an undefined value. This you're going to have to memorize. Okay, this has to do with your answers. The range is your answer that you're going to be looking for through a drawing. You can only be between pi over 2 and negative pi over 2 with your inverse sine. In fact, you cannot even spin through these areas at all. You're only allowed to travel from here to here or from here to here. Don't even come over here when you do your drawing, and don't spin through those quadrants. So those are the restrictions. This is called, some vocabulary for you, this is called the explicit form when you can see the inverse symbol. And this is called the implicit form when you rewrite this without the inverse symbol. And let me point out, if you're not noticing this, that all it takes to go from inverse form to non-inverse form, you're always going to write it in the non-inverse form when you go to solve and find the angle that you're going to be looking for. All you have to do is switch the x and the y. And they're using y to mean the angle that you're looking for. You're probably going to want to write it as a theta, just, for clarity in your mind. But all you do when you want to get rid of this inverse symbol is switch these two. So the x would come over here where the y is, and the y would jump over and take its place. But like I said, this is actually what you're going to be looking for, your answer, and it needs to be in there. I just included a little picture for you here. I wanted you to remember that an original portion of the function, which was this portion in blue up here, that's what you're seeing in this picture. And this is a corresponding picture of the inverse. You're not going to be graphing the inverse, but the graph of an inverse and the original and the portion from the original graph, they always form mirror images on either side of the line called y equal to x. And those mirror images are like this. This looks like a kind of a sideways parabola, and then this one is the same shape and size, but on the opposite side of y is equal to x. You won't have to do that, but that is true of all inverses, that they form mirror images over the line, across the line, called y equal to x. And the other thing that I would like you to know for inverses has to do with, and inverse sine specifically, has to do with these composite functions right here. But I think what we'll do is any of the regular inverse sine problems, and then we'll come back and catch these. What happens when you have an inverse as part of what's called a composite function, a function substituted inside of another function. So let's just go first and pick up the ones that are regular inverse sine, and then we'll do the double composite functions that involve inverse sine. So we have one right here as the very first one. This says they really just want you to rewrite this. So what does it mean? And they're talking about the domain of the inverse function and the range. They've already stated that for you. When you rewrite that, tried to point out to you that all you do is switch these. So really simple, going from inverse form to non-inverse form. You're always going to want to get into this form before you solve the problem. So that would be right there. And let's see, what else do we have here? Number 3, those are composite functions, so we'll wait on that just a bit. But here's a simple one for number 5. You're just finding the inverse sine of 0, so let's begin with the kind of things that you need to be thinking about. Okay, first of all, you need to know that you can call this anything you want, but it's an angle. I thought maybe if you put a theta, it would be clear in your mind that you're looking for an angle. Next thing you're going to want to do is rewrite it. Rewrite it in its non-inverse form so that we can read it to ourselves and make some sense of it. That just takes switching these two things right here. Let the theta come over here and the 0 jump out and be by itself. So its sine of some unknown angle is equal to 0. Then you're going to want to draw. You want to create a drawing where you are looking for the angle whose sine value is 0. Okay, you're not going to be able to draw a triangle because anything to do with zeros and ones has to do with the unit circle. So let me remind you of those values. If you're on a unit circle where the radius is 1, that means it's 1 to go out to this edge of the circle with the y-coordinate being 0. If you're up here, the coordinates are 0, 1. Again, the radius being 1. If you're over here, it's -1, 0. If you're right there, and if you're right here, you're at 0, -1. Then a student who is successful with this problem needs to remember that the x-coordinate of each of these points is considered the cosine value, while the y-coordinate is considered the sine value. And in knowing that, you are able to answer the question. Where have you rotated to? That's what it means to find an angle. Where have you rotated to such that the sine value is 0? That would have to be right here. This is the only location of the 4 that I've just labeled for you where the sine value is 0. Because it's not 0 there. It's, let's see. It is 0 here, but let me tell you why that is not going to be an answer for this. So give me a good opportunity for us to talk about that. And it's not 0 there. So it's 0 here and 0 here. Let's talk about or remember that with these problems, you're restricted to a particular zone. And anytime you are looking for an inverse sine, I would suggest getting yourself a marker and keep highlighting it until you memorize it. For inverse sine, you need to be right in there. It's the only place you're allowed to give answers. So the reason why this is not an answer, even though the sine value is 0, is that it's not in the restricted zone and therefore it wouldn't be defined as part of the answer. So where are you when you're right here? You're at 0 degrees. Or you can just put 0. 0 degrees can be written with a degree symbol or no symbol at all. So the answer here, 0. Okay, let's see if we can find any other ones. Here's another one. Regular inverse sine. This will give us a chance to think about it a little bit more because now we will be able to draw a triangle. You just can't draw a triangle when it involves zeros and ones. It'll be something that is right on an axis. Okay, so here, again, you're looking for an inverse. That means you're looking for an angle. Now rewrite it. When you rewrite it, that just means you get rid of the inverse symbol, and that happens simply by switching the theta with this number, just switching their positions. So the theta is going to come right up against the sine, and the square root of 2 over 2 will jump out and take its place. Now you're going to draw it. Remember, you are looking for an inverse sine, and therefore you need to be in the restricted zone, which is here to here. Maybe you can think of this as a banana belly. This will be pi over 2. This will be negative pi over 2. Wherever you draw your triangle, it either better be in quadrant 1 or quadrant 2. But notice now, since we're not talking about zeros, we can talk about positive and negative. This is a positive value. The sine cannot possibly be positive down here. Because remember, the sine's like the y value. It's even defined as y over r. So that can't happen that you're getting a positive sine value down in quadrant 4. Therefore, your drawing is in quadrant 1. Okay, let's go put this where it belongs. We're going to let the sine value be square root of 2 over 2. And I think you know what reference angle goes with that. A lot of you are getting pretty good with this. That when the sine value is square root of 2 over 2, so is this. You're in a unit circle. This is 1. Therefore, the reference angle has to be 45 degrees. The reference angle is always right there at the origin, or we could also call it pi over 4. And you're going to want to get used to giving these answers in pi units. Okay, so that reference angle can be called 45 degrees. I'm going to try and really make a point with you about what is the difference between the reference angle and the real angle. The real angle is wherever the arm is that creates the hypotenuse. When you're in quadrant 1, and only when you're in quadrant 1, will the reference angle and the actual theta, which is going to be the answer that we're looking for, where this arm actually is. Only when you're in quadrant 1 will these two be the same. But once you get over here or anywhere else other than quadrant 1, then the final theta, which you're shooting to find, and the reference angle won't be the same, only in quadrant 1. So, because we're in quadrant 1, we have actually found that final theta. Okay, let's go ahead and look at and see if there's any others here. Okay, looks like the rest of them are composite functions having to do with inverse sine, so let me go ahead and throw that at you. The definition for that would be right here. Composite functions, as I said, are double functions, one function substituted into another. And what you want to look at for these problems is you want to look at, is there an inverse sign on the outside or is there a regular sign on the outside? Because that will dictate the restrictions for that particular type of composite function. When the inverse is on the outside, you go by the restrictions of the inverse. And those again are negative pi over 2 to pi over 2. You can even keep drawing that little drawing if you want to remind yourself. You can be anywhere from here to here. Excuse me. If sine, regular sine, is on the outside, then you go by the domain of regular sine, which is that it has to be between -1 and 1. Okay, so we're going to look at those and stick to those restrictions as we do any of these composite functions. You're going to notice that in the case of these composite functions, that if I do give you inverse sine on the outside, those can be redrawn so that the problem is doable, although it may appear not to be doable at the beginning because they're throwing you something that's not in the restricted zone, whereas these cannot be redrawn. If they give you the wrong value in here, it simply shuts down the problem. That's when regular sine's on the outside. So let's look at those, and I will try to even give you more detail on that as we hit those problems. Okay, so let's see. Going back to the first page, we're not ready for that one yet, but we can do number 12. Okay, so again, let's look at this. When inverse sine is on the outside, the value that they give you right here has to be between negative pi over 2 and pi over 2. And as long as that value is between here and here, then you can go on with the problem. Once you get that value right in there, this simply takes this out. They cancel, as inverses are the opposite of the original function. So they would cancel, and the answer to the entire problem, once you get the appropriate value right there, something between negative pi over 2 and pi over 2, would just be that value, whatever is here. Okay, the problem, or the issue with number 12, is that as soon as you start this problem, you look at this value right here and hopefully realize that it is not in that restricted zone between pi over 2 and negative pi over 2. You're supposed to be right in here with this value in order to allow you to go forward with this problem whenever inverse sine is on the outside. Yet think about it. If you were to rotate to 9 pi over 8, you would be at 8/8. That's what 1 pi is. And then you'd have to go 1 extra eighth. So you would have rotated to 8/8 and then an extra eighth to get you to 9 pi over 8. And so you see where you are. You're over here down in quadrant 3, yet you only had permission to be in here. So you have broken the restriction, and therefore you cannot continue with this problem until you rectify this value right here. You need to get it to be a value in here, and then you can do the inverse sine of the sine. So as you redraw this problem, you're going to want to mimic all the things that are happening here, or as closely as possible. Number 1, you're going to want to get the same reference angle, which is pi over 8. Number 2, you're going to want to ask yourself, if I was in quadrant 3, what would the sine value be? Would it be positive or negative? When you're in quadrant 3, remember, the sine value is the same as the y value. Y values down here in quadrant 3 are negative. So if y values are negative, the sine value is negative. So you're also going to want that to happen. You want the reference angle to be pi over 8, just like it is in the original rotation. You want the sine value to be negative, just like it is in the original rotation. And then you also want to be in this restricted zone. So you're going to redraw the picture, making all of that happen, and then you'll have permission to do the inverse sine of the sine. So let's create a picture that makes all those things happen. Let's stay right in here. We want the sine value to be negative, therefore we can't be in quadrant 1 because in quadrant 1 all of the trig values are positive. So we're going to have to be down here, meaning that we've rotated this much, and the amount that we've rotated, of course, is the reference angle, because that's always this angle right here with its vertex at the origin. So we have rotated this way. This is the reference angle, but where this arm actually is, that not only signifies how far you've rotated, but in what direction you've rotated. So there's a difference. There is a difference anytime you are in any quadrant other than quadrant 1. The reference angle and the regular theta, the actual theta, there will be something different about those two things, either by, it might be a sine, or they might be completely different values, but they won't be the same. Okay, so now we're going to rewrite this problem, and we'll now be able to do it. We're in the restricted zone. We have the reference angle the way we want to, and we're in a quadrant down here where the sine value is negative. So we've made all the things from the original problem. We have replicated them, and now I'm going to rewrite this problem so that it's actually doable. I'm going to do the inverse sine. This situation that you've created here, this negative pi over 8, will replace that undoable 9 pi over 8 that they had given us. And it happens to be equivalent. If you were to put those in the calculator, if you were to put sine of 9 pi over 8 and sine of negative pi over 8, you would get the same answer. So now the inverse sine actually cancels with sine, and now that this is in the appropriate zone, that is the final answer. And you can skip this part if you want, because once you redraw it, that new angle is the actual answer. Okay, so that's number 12. That gives you a composite function. And let me see if there's any others here. I think that's all for inverse sine. Okay, now we're going to go to inverse cosine. Here is a picture of what the original cosine graph is, just very similar to the sine graph, only it starts at 0, 1, whereas the sine graph starts at 0, 0. But it is cyclic, same issue. Fails the horizontal line test, just like the sine graph does. So we're going to, just like the sine function, going to remove just this portion right in here that I've highlighted in pink, but removed for you over here. And in removing this portion, it now passes the vertical line test as well as the horizontal line test. For this portion that we've removed from the original function, the domain is 0 to pi and 1 to negative 1. But the domain and the range switch responsibilities once you start going from the original function or any portion of the original function to talking about the inverse. So what you see here as the domain is now the range in terms of looking for the inverse, and what you see here as the range is now the domain, because that always happens. That's the relationship that original pieces of a function and inverses have. Okay, again, I wanted to point out to you that you will always be going for, you'll be presented the problem like this, where you'll be looking for the inverse cosine of some value. For inverse cosine, it still needs to be between negative 1 and 1, just like for inverse sine, and this will be the angle you're looking for. So you could always write a theta there instead of a y, just so you don't get confused. Once you go from inverse format to non-inverse form, All you do is switch the x and the y, just like I showed you for inverse sine. This pops over here, this takes its place. And then you'll begin the problem. What's different here is the restriction. Your answer has to be between 0 and pi. And the reason I color in the endpoints whenever I do is because those endpoints are allowable as part of your answer. If I draw a circle at a certain point but leave it hollow, it's because those answers are not acceptable. Those endpoints are not acceptable, but anything in between is. Okay, so maybe you can memorize this, the answers that you're allowed for inverse sine, kind of like a banana belly between pi over 2 and negative pi over 2, just as it says right here. And then maybe you can memorize this one as a sunrise. Banana belly, sunrise. Okay, there are also composite functions for inverse cosine. And much the way I explained the composite functions having to do with inverse sine, I can pretty much hit this the same way. You have different restrictions for when you have the inverse cosine on the outside as opposed to when you have regular cosine on the outside. When the inverse cosine is on the outside, you'll go by the inverse cosine restrictions, which are sunrise, 0 to pi. And when regular cosine is on the outside, you'll go by the restrictions for the cosine functions, the domain, which is between -1 and 1. Okay, so let's do anything having to do with inverse cosine or the composite. Okay, so when you get to, let's see, number 2, right away you have a composite. And it looks like they're just trying to get you to complete the definition, so we can look right on there. When you have the inverse cosine on the outside, the restrictions have to do with that outside function, which is anything between, I had given you a visual on that, it's the sunrise visual. That's between 0 and pi. That's that one right there. Okay, then let's go to this one, number 3. Which you needed to know things about the composite inverse sine as well as the composite inverse cosine. Okay, so let's see. When regular sine is on the outside, this value, you can look at your theorem section as you go along. This value needs to be between -1 and 1. It is. And when it's in the expected restricted zone, these just cancel. So this would be equal to 0. So that's true. But for us to say true, both of these have to be true. When you have regular cosine on the outside, again, it's restricted. This number should be between -1 and 1 for you to go on with the problem. It is. And therefore these cancel, and this is equal to 0. So this is true. Both statements that they've given you are true. We have not done inverse tan yet, but that'll be the last inverse that we do in this section. So let's go to number 8. Okay, number 8. You're going to follow all the same steps, but you're going to just use a different restriction. Okay, when you're doing inverse cosine, it's the sunrise. But you start off looking for an angle, just like as if it was a inverse sine. You rewrite it in the non-inverse form. So it'll just be regular cosine of theta and swing that right out there and take its place. These just switch places. So this is negative square root of 3 over 2. This will really give me a chance to distinguish between reference angle theta and real theta. We are looking for the final theta, which we need to look at reference angle first. So we've done that. Then we're going to draw. But we're going to recall the restrictions. You're allowed to be anywhere from here to here. So you're either allowed to be in quad 1 or quad 2. You may not be here or here. You want this to be true. Remember, cosine is their x value. In fact, from chapter 6, it's defined as x over r. And if we're in a unit circle, the r is just 1. So we can really think of cosine as just x. You can't be in quadrant 1 because nothing's negative over here. There are no negative trig values here. So you have to be over here with your rotating arm. This rotating arm represents the theta that we will ultimately be looking for. We can't find that theta until we find the reference angle. So you may want to close this up and drop down to create a triangle. If this is the cosine value, that means it belongs on the horizontal leg. And if this is your, square root of 3 over 2 is always the long leg. If that's your long leg, then this has to be 1/2. Whatever the value is along this vertical leg, that is the value that determines the reference angle. Okay, this is the short leg. Across from the short leg is always the 30-degree angle. So this reference angle is 30 degrees, also known as pi over 6. I just write these in pi form because they always want them in pi form, so you might as well get good at that. Let's just keep practicing that. Okay, so if I really want to know what theta is, but yet all I know is the reference angle right now, what I have to practice is counting in fractions. Okay, once you rotate all the way to right here, the negative x-axis, you're at 1 pi. But 1 pi is also called, let's see, what are we talking about for the reference angle? 6s? This is also called 6 sixes. Just as a landmark that this negative x-axis represents 6 sixes. So if you were trying to decide where have you rotated to in order to get a hypotenuse that's right there, 1/6 before you got to 6 sixes, that means that this rotating arm, which is ultimately the answer, where the hypotenuse is, that's ultimately the answer for the actual theta, which is 5 pi over 6. Okay, you were rotating, as I said, you stopped here 1/6 before you got to 6 sixes. If you had rotated all the way to the negative x-axis, you'd be at 6 sixes, but you stopped. This blue arm stopped 1/6 before you got there. So anytime you stop right before you get to a landmark, you will be doing subtraction, although you may be doing it in your head. It'll just be the landmark, 6 sixes, minus the reference angle, and that'll give you the theta. It has to be a number less than 6 sixes, which 5 sixes is. Again, notice that when you're not in quadrant 1, the reference angle and the real theta are different. Sometimes they're different by virtue of a sign, and sometimes they're just completely different numbers, as you're seeing right here. I've given you both cases already. I don't believe I did number 9. I think I skipped right over that. So why don't we go ahead and just stick that in since we're on it. Inverse sine of 0.8, you find the value in radians. That means your mode should be in radians. And good thing about your calculator, you can use your calculator to check even these ones that you're drawing out and you're doing by hand. I mean, like for instance, first let's do number 9, inverse sine of 0.8. So let me see if I'm in radians first mode. I'm in radians. Let me quit out of here. So second inverse sine, and we're doing 0.8. You can just put 0.8 in there, and you get 0.93. They want you to round to the nearest hundredths place, so 0.93. What I did want to tell you is, though, even though this doesn't say to do it by calculator, which means every time it says find an exact value, that means I want the drawing. I want the drawing, and I want you to show me that you understand everything you learned in chapters 6 and 7, that you know what a reference angle is, that you know the difference between the reference angle and theta, that you know how to put values on the sides of triangles that dictate what the reference angle is and thereby help you to find the final theta. I want you showing all that work, or else the problem is not complete. However, you can use your calculator as an answer key. If you want to just put this in, I mean, if you were going to try and figure out what this was as degrees, you could go 5 times 180 divided by 6. Look what your answer is. 5 times 180 divided by 6. It's 150 degrees. Whoops, sorry about that. So this answer is 150 degrees. So if you were to put your calculator in degree mode, just to check to see if this 5 pi over 6 that you got is correct, and let your calculator tell you the answer. That will kind of serve as an answer key. You could go mode, you can go degree, second quit. Let me make sure I got my, I'm still in radians. So degree, I didn't press enter. Second quit, and you can go ahead and press this in now, and it'll give you a degree type answer. We already know that this in degrees, because I just stepped off to the side and converted it, is 150. So if this is right, I should get a 150 in here when I press it into the calculator. So second inverse cosine, and then just press in negative square root of 3 divided by 2, close that up again. See? Get 150, and the answer that you got is 150. Okay, it's just that you're not allowed to do the whole thing by calculator. You have to actually show that you know what you're doing as far as rotation. Okay, let's see what's on this next page. The only ones that we can't do so far are the tangent. I just haven't introduced that to you yet, but we'll be able to do it in a minute. So let's go to 11. So problem number 11, find the exact value. Do not use a calculator. Okay, so for inverse cosine, we just have to remember what the restrictions are when the inverse cosine is on the outside. Inverse cosine, let's see, we're allowed to be anywhere from here to here. All right, and you understand that this angle right here actually is between here and here. See that? Some of the other problems that I've done that have been a composite function like this, they didn't give me an angle that was in the restricted zone, and so I had to go through some moves in order to redraw the picture and rewrite the problem so that it was doable. However, this one's a piece of cake because this is 1 pi right here, 9/9 when you get to 180. And you've only been asked to rotate to 7/9. So you're right in here, which is in this restricted zone. And when that is the case, that they give you an appropriate value in the restricted zone, you can just flat out cancel those, and the answer is equal to whatever this is. So your final answer, 7 pi over 9. It's just that in order to be able to cancel inverse with regular cosine, or regular sine with or inverse sine with regular sine, that this just has to be in the restricted zone. Otherwise, you got to go through that extra work that I did for this problem. Okay, let's see. Wait, it's possible the rest of them are tangent. Wait, here's another one right here. Okay, so here's another composite function, and so it's number 15. Whenever regular cosine is on the outside, you have to be between, the x values have to be between -1 and 1. Okay, and of course this is 0.4. You can just go 2 divided by 5 in your calculator if you don't already know that. So this is in the restricted zone, and as long as that's the case, there's really no work. You just have to know whether this is in the restricted zone or not. These just take each other out, and this is equal to 2/5. Or you could put 0.4. It's whatever the value is there. Okay, blah, 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 blah. So let's put that right there. Number 15, again, you have cosine on the outside. You have to know those restrictions. This has to be between -1 and 1. Although as soon as you press this in, you're going to know you're in a problem. Because if you went to go press that in, if you weren't sure what the restrictions are, let me put a little equal sign right there. You see that number? It's not between -1 and 1. It's too big. But if you were to try and press that in, second inverse, and you put in a 1.9, see, it quits on you because it knows that it's too big. So this would be undefined, and that's because that is too big. It's not in the restricted domain for this kind of composite function. Okay, last thing that we need to go over is inverse tangent as well as the composite functions, composite function definitions and restrictions for inverse tan. So inverse tan, much in the same as inverse sine and inverse cosine when you just have a single inverse tan. If you want to go from inverse form to non-inverse form, you switch the x and the y, just like this. Only this time, the values for the domain, which are really the range values from the original function, you know, that's a wave that climbs up to infinity and down to negative infinity. So those range values on the original function are now the domain values for the inverse. So when I give you an inverse function, I can give you any value to start with. Unlike inverse sine and inverse cosine, it doesn't need to be between -1 and 1. Okay, so that's a little bit different. Where you're restricted to is the same as inverse sine, only the endpoints are not allowable as final answers. Okay, so like the banana belly, the endpoints are not allowable as answers. The composite functions, which are the double functions, one function plugged into another, will either have inverse tan on the outside, and when it does, you're going to go by the restrictions for the inverse tan, which I just gave you a picture for right up here. It's like that. Inverse sine, only you cannot use the endpoints. Okay, and when regular tan is on the outside, you will use the domain for regular tan, which is negative infinity to infinity, which is actually the range of the original function. But so those are the restrictions. Let's go to the rest of these problems. Okay, so in problem number 4, that's the only one remaining on the first page. It means this when you rewrite it. Just put the x over here and the y over here. Interchange those to go into the non-inverse form. X can be in between negative infinity and infinity. They've already put the restrictions here for you, and that is true. And y is between, or actually I think they have those, I think they did have those switched around. Oh, no, they have that right. The x is between negative infinity and infinity. I thought they were messing with us for this one, but here's what the x has to be. Okay, so the x has to be between negative infinity and infinity, and y has to be between negative pi over 2. I'm looking at those and thinking they switched them. No, they have it correctly. Okay, so then let's go to where we're actually calculating values, which is what most of these problems are about. There's very few where you're not doing that. I don't know how crazy or how stuck I'm going to be on the composite type problems. I tend to give way less of those, but the main point in this section is being able to do this. Evaluate for a single value of an inverse function. Okay, so here we go with the zeros and ones. We will not be able to draw a triangle because there's zeros and ones. You are looking for an angle. You just have to remember where you're restricted. So remember for inverse tan, you are restricted from here to here. All right, so let's think about it. Right here, you have values of 1 and 0, being that you're on a unit circle. You can't give that answer, and you're looking for and you can't give an answer here. So it has to be this answer, but you can check that. Tan is, when you rewrite this in a non-inverse form, the theta comes here and the 0 takes its place. These switch. So it would be tan of some angle, some rotation location, is equal to 0. Tan is the same thing as y over x. So whatever you're going to give for an answer, whatever location you're claiming that you rotate to so that the tan value is 0, you should be able to go y over x and get a 0. And of course you can. When you go y over x, you do get a tan value of 0. See? So it works out there. Where is it that you've actually rotated to if you're sitting right here at this point? 0 degrees. So the answer is, you can just put 0 or you can put the degrees on it. I would just put the 0. Okay, I think I've done all the problems on that page. This one is a calculator problem. So inverse tan, they want it in radians. So make sure that your mode is in radians. So I can quit out of there and then go inverse tan, second, inverse tan, just press the tan key, press in the number that they've given you, which is negative 4.1. Make sure with this answer that you are in the restricted zone, because if you're not, you have to use it to get in the restricted zone. So the only thing you got to be careful about. Okay, this is negative 1.33. Again, for inverse tan, you can be anywhere from here to here. Okay, so for inverse tan, if you were to rewrite this, it would just be tan of theta is equal to a negative value. Negative tan values don't exist here, so you're down here. They have said that the rotation here is called theta, because the calculator is giving you the theta. They're saying that that's negative 1.33, and that is definitely within the restricted zone, because this one's called pi over 2, which, by the way, is 3.14 approximately divided by 2. That's about 1.58. And this is the negative version of that, negative pi over 2. You definitely get to negative 1.33 before you get to this, so you're right there in the required zone. So negative 1.33 can be given as your final answer. You always want to check it even when you're getting it from the calculator. By the time you get here, again, just make sure that this is in the restricted zone, because if it is, for a composite function with inverse tan on the outside, you have to be in between here and here for it to not be much work. And when you get to this problem, it is not. So this problem is on the same level as number 12, where we had to do all this redrawing and rewriting in order to make the problem doable. See, in this problem, they gave us a value that was not in the restricted zone. That is the same thing that's happened here. So again, these are both on the same level. How do I know? Because when you go to 6/7, you're over here. This is 7/7, 1 pi. So 6/7 would be about right here. And when you're over here at 6/7, look at the things that are happening. Your reference angle is 1 pi over 7. It's 1/7 before you got to 7/7. That's where 6/7 is. So your reference angle is pi over 7. As far as the actual tan value at 6/7, look at the quadrant you're in. Tan is y over x. And when you're in this quadrant, x's are negative, y's are positive. So when you go to do this, you're going to get a negative tan value. You could also use that saying that I gave you. All students take calculus. When you're in this quadrant right here, the only thing that's positive, because that's what that saying is about, the first letter of each word tells you about the trig functions that are positive, not negative. So all students, S in students means the sine function is positive, and cosecant, which is made out of nothing more than sine. Everything else is negative, such as the tan. So you're in a quadrant here and where tan is negative. Okay, so you want the reference angle to be pi over 7, you want your tan value to be negative, and you want to definitely be in the restricted zone. You need to make all these things happen before you can actually make this problem doable. Okay, so let's redraw. We're going to keep it in here. We're not going to be at those endpoints with our answers. We want our tan value to be negative. And I only have a choice of these two quadrants. Nothing is negative in quad 1, so I need to be down here. I know that my reference angle has to be pi over 7. And even though this is the reference angle, that is not necessarily this theta. Because when you're in any quadrant other than quadrant 1, the reference angle and the real theta are different. Okay, what's different about them here is just the sign. If you rotated this far from the x-axis, yes, you would be at pi over 7. But to avoid spinning through these quadrants, you would have to spin negatively so that you land in a quadrant where the tan values are negative and you don't leave the restricted zone. So you have to put that negative there to show that you spun in a negative fashion. So, I mean, you could rewrite this as inverse tan of negative pi over 7, but, I don't know that you need to go through that part. Once you find this new angle that satisfies this, and this, that's the answer. Okay, so that's 13. See if there's anything left undone. I did 14, 15. That looks like that is it. So that completes